6 times between 1969 and 1972, humans walked on the moon and came home. Then we stopped. For more than 50 years. Now we're finally going back. And the first mission meant to put a crew on the moon isn't going to land. Not because we forgot how, not because we've gotten worse at engineering, but because going back is different now. It turns out it's a harder problem than getting there the first time, and the whole thing hangs on a single move that no one on Earth has ever made. Let's dive into it. To see why it's harder now, start with why it was simpler then. Everything Apollo 11 would ever need was already aboard a single rocket. Fuel to reach the moon, fuel to land, fuel to climb back off the surface, fuel to get home. All of it lit in sequence and dropped away in pieces as the mission went. That worked because the lander was small. Fully loaded, the Apollo lunar module weighed about 15 tons. Light enough that the Saturn V, the largest rocket anyone had ever built at the time, could throw the entire stack at the moon in one launch. One launch, one shot. Nothing held in reserve. Nothing left waiting overhead. Nothing carried home but the crew and a few boxes of rock. That is the design we are deliberately not repeating. And the reason we're not repeating it is the whole story. The word we're walking away from is disposable. This time the goal isn't to visit, it's to stay. To come back again and again, and eventually to keep people up there. And a moon program you actually keep needs a lander you don't throw away after one trip. That single choice breaks the Apollo math. The lander being built for the job is the size of a 15-story building. It's meant to set roughly 100 tons on the surface, 6 times the entire loaded weight of the Apollo lander, and then fly back up to orbit to be used again. But again is the expensive word. To land, lift off, and return, it has to carry an enormous amount of fuel. And rockets punish that without mercy. You want a vehicle that can do more? You need exponentially more fuel for that. Add it all up, and a fully loaded lander needs something like 1,200 tons of propellant. Here's the trap. The rocket that lifts it can carry maybe 100 to 150 tons to orbit at a time, and in its 2025 test flights, far less even than that. So the lander reaches orbit nearly empty, and someone has to fill it up there, in space. Which sounds like a detail, but it's one of the hardest parts of the entire program. Pour fuel into a tank on Earth, and gravity does the sorting for you. Liquid settles low, gas floats high, a flat line between them. Open a valve at the bottom and you get liquid. In orbit, nothing settles. There is no bottom. The fuel smears across the walls in a film, clumps into floating blobs, breaks into a slow churn of liquid and gas with no boundary anywhere, like a lava lamp that never picks a side. Open your valve and you don't get a clean stream. You get whatever drifts past. Liquid, vapor, or a useless mix of both that no engine can burn. So before you move a single drop, you have to invent a bottom. Both ships fire small thrusters and creep forward, about 1,000th of normal gravity, just enough to make the fuel drift to one end and pool. Now there's a surface and you can pump. But that nudge costs fuel. You burn propellant to settle propellant just to earn the right to move it. And even once it's flowing, the clock is already working against you. The fuel is cold, brutally cold. Liquid methane has to stay near 111 Kelvin, about minus 160 Celsius, or it stops being liquid at all. And space, for all its reputation, will not keep it there. The sun scorches one side of the ship. The earth below glows with infrared heat, a warm wall you're parked against. More heat seeps in through every strut and pipe, so the propellant slowly, constantly boils. And the boil-off builds pressure you have to vent, which means dumping fuel overboard just to keep the tank from bursting. This is even why they chose methane. The obvious alternative, liquid hydrogen, has to be kept 5 times colder. And hydrogen molecules are also so small they leak through metals that would hold any other gas. So methane was a deliberate choice. And it can't be done slowly either. Every day the fuel sits up there, more of it escapes, which turns the whole operation into a race. To outrun the boil-off, the tankers have to launch about once every 6 days. Somewhere near 10 flights of the largest rocket ever built, packed into roughly 2 months. No one has ever launched anything at that pace. Not the Saturn V, not the shuttle, nothing, ever. And how many flights exactly? Nobody agrees. SpaceX once said 4 to 8. Government auditors said 16. They're all speculating, because the honest number depends on things nobody has measured yet. Which is the quiet truth under all of this. The entire plan rests on a step that has never once been taken. So, is any of this actually new? Partly, no. Refueling a spacecraft in orbit was first done back in 1978, when a Soviet supply ship docked with a space station and pumped propellant aboard. Russia has done it routinely ever since. China refueled a satellite tens of thousands of kilometers up in 2025. Passing fuel between 2 craft in orbit is by now almost ordinary. But every one of those used storable fuel, the easy kind, that sits in a tank for years and behaves. None of them moved cryogenic fuel, the super cold kind. That's the line no one has crossed. The closest anyone has come is SpaceX itself. In 2024, one of its ships moved about 10 tons of cold propellant from one of its own tanks into another, the largest cryogenic transfer ever done in space. But it was one ship, one set of plumbing, no second vehicle, no docking. Doing it between 2 separate ships, joined in orbit, the exact move the moon mission is built on, has still never happened. It's promised for 2026, and that date has already slipped. In early 2026, NASA announced it was adding a mission to the program. The first flight that was supposed to land, Artemis III, would no longer land at all. Instead, it would stay in Earth orbit and rehearse docking with a stripped-down test version of the lander. The landing itself slipped to the mission after it in 2028. There's a precedent they pointed to on purpose. The mission flown just months before Apollo 11, which tested the lunar lander in Earth orbit before anyone dared try it at the moon. Same idea, 60 years apart. Officially, NASA called it caution, a smaller, safer step before betting lives 250,000 miles away. But there's a simpler reason there was no landing to attempt. The lander isn't ready, and the piece that isn't ready is the refueling. It has never been done between 2 ships, and the test meant to prove it keeps sliding. So, we did this 50 years ago, 6 times. Why is it so much harder now? Because we are no longer trying to do what we did. Apollo was a sprint. Land, grab some rock, come home, throw the machine away behind you as you go. At its peak, the program consumed more than 4% of the entire federal budget. And the instant it won the race, it ended. It never refueled anything, because it never meant to stay. This time, staying is the point. A lander that returns instead of crashing. Visits measured in weeks. One day, a base. And the moment you decide to reuse the lander, the math leaves you no way out but to refuel it. And refueling drags in every problem we just walked through. We aren't worse at this than the engineers of 1969. We're reaching for something they never attempted. They asked whether we could get there. We're asking whether we can stay. and the first time two ships quietly trade cold fuel in orbit. No crew, no flag, no footprint, no one watching. That won't be a footnote. That will be the first real step back to the moon.